focusing on the key concepts of dynamic programming, how we can identify dynamic programming problems, and then we can go through different techniques we use and practical applications of dynamic programming. So this session is for everyone, whether you are preparing for this year's IEEE or you're just looking to expand your knowledge. This session is designed to enhance your knowledge and your problem-solving skills. So today, the session is conducted by Miss Master Thimira Hirushan, who is a final year electrical and electronic engineering student from our very own University of Peradeniya. So his team was ranked 27th in the country during last year's IEEEXtreme 17.0. And so if you have any session, if you come forward with any questions while we are doing the session, so there will be a Q&A session after everything, after our presentations, and then you can either unmute your mic and ask the question, or you can type it out in the chat box. So I can read the questions to Thimira and he can answer your questions. So with that, I invite Thimira to start with the session for today.
Okay, thank you, Anaga. Can you hear me? I think I'm audible.
Yes, you're audible.
Okay, thank you. Then first let me share my screen. Yeah. Okay, I hope you can see my screen as well.
Yes, we can see the screen.
Okay then. Thank you for inviting me. And then again, good evening, everyone. Now I'll start my session on dynamic programming, which is main concept that we learn when we are preparing for a programming competition, or when we are learning competitive coding, how to solve problems using competitive programming techniques. Most probably, we in most of the cases we need to know this concept, because this is such an important concept when you are solving a competitive programming problem. With dynamic programming, in many cases, you would be able to simplify the problem, and also you might be able to reduce the time that is required to solve a problem drastically by using this dynamic programming techniques. So first of all, I will take you through the plan. So we are going to discuss about key concepts of dynamic programming. What is it? What is it called dynamic programming, and how to apply dynamic programming, and what should we know to use dynamic programming techniques. Those things we will discuss first. And after that, the most important thing, how can we identify a dynamic programming problem, and after that we will discuss how to after identifying the problem, how we can apply our knowledge to solve a dynamic programming problem, or any other problem that can be solved using dynamic programming. Right? So after discussing how we can apply it, then we will discuss some examples about dynamic programming that we can where we can use dynamic programming. Like there are problems where you can use dynamic programming directly and indirectly. So we will discuss about them later. After that, though, while the session is going, you can point out any questions you may have, so we can discuss those as well. Right. Okay. Then first I will move on to the key concepts of dynamic programming. So first of all, we need to know what is called dynamic programming. So first of all, I will explain what dynamic programming is. So normally, in a programming, when we are solving a competitive programming question or some problem, we are executing some code, right? So in that code, we are doing some set of operations. So during those operations, if we are doing the same thing again and again, right, that is completely useless. If we can remember that we have done this thing earlier, and then we can call the memory and go back to that place, and again, if we can take that in, that is very useful, right? Uh, that is called the that is like a repetition of calculate. So if we see a repetition somewhere, then what we have to do is, if we remember what the answer, we can call it back and then take it into the present case, right? That is one thing where we meet a repetition of calculating values, right? Another thing is, if we find somewhere, we can divide a problem into small subproblems. Like I have a good example here for both those cases. We can take this one as an example. So the example I have here is a Fibonacci sequence, right? So I hope you all know the Fibonacci sequence. Anyways, first of all, I will tell you what the Fibonacci sequence is. So Fibonacci sequence, we will consider the case where it starts with 2 ones, right? So in the Fibonacci sequence, we have to define the first 2 terms. Sometimes it will be 0 and 1, or otherwise it will be 1 and 1 most of the cases. So here the Fibonacci sequence continues adding up last 2 terms and making the new term like this. In here, 0 and 1 are the first 2 terms. You have to define it. After that, you have to add the last 2 terms. So 0 plus 1 is 1. 1 plus 1 is 2. Then 1 plus 2 is 3. Then 2 plus 3 is 5. 8, 13, and so on. So this way, you can go up and up in the Fibonacci sequence. So I take this as an example, but sometimes you may find lot like a lot more optimized way to find the nth term of Fibonacci sequence. But you can use dynamic programming to find the nth term of the Fibonacci sequence as well, right? So I will explain how we can find the nth term of the Fibonacci sequence. So in order to find the nth term, you must know the n minus 1th term and n minus 2th term, right? So in order to find the nth term, you have to find n minus 1th and n minus 2th term. So that brings up the idea of solving subproblems. Like you are going to find the nth term. In order to find the nth term, you have to find n minus 1th term and n minus 2th term, right? So that is one way we can see dynamic programming. So you are instead of solving the greater problem, you are solving some problem which is less complex or which is lower than that main problem, right? So that is one concept in dynamic programming. The other one is you have to memorize the answers. So memorization is mainly uh, involved in dynamic programming. So what you are going to do is you are going to divide your problem into some set of sub problems. After that, you are while you are solving those sub problems, you are going to store those answers in the memory. So you if we encounter the same problem again and again, you can just call your memory, right? Okay, I will show you this Fibonacci example. So if you are finding the seventh Fibonacci term, like we start with 1, 1. So 1, 2, 3, 4, 4, 5, 6, and the seventh term is 13. So here the seventh term we have to find. In order to find the seventh term, we need sixth and fifth terms. So in order to find the sixth term, we need again fifth and fourth terms. To find fifth term, we need again fourth and third terms. Again, third term, and first and second term we have to define by our, because in Fibonacci sequence we are defining first two terms. So in this case, you saw that in the recursive approach, we are solving like we are finding the sixth Fibonacci number and fifth Fibonacci number. So when you go into the recursion, you are going into again finding the Fibonacci number of n minus 1. Here you can see in this code, but I will show you a complete example later. So in this case, you will find fifth and fourth one as well. But here you are finding the fifth Fibonacci number, and this side as well, you will be finding the fifth Fibonacci number. So actually that may be useless, right? Because if you can remember what fifth Fibonacci number is, then what you just have to do is you have to recall it, right? You don't have to calculate it again. If we think about this third Fibonacci number, you are going to find it like around 5 times if you are not using dynamic programming. So if we use dynamic programming, you will have to calculate only 5 terms in order to calculate the seventh term, right? Because first and second we already know. But if we don't use dynamic programming, you will have to calculate all these like rounded uh, calculations, right? So that is why memorization or the memorization is important, and this dynamic programming is important, right? If you are solving a larger, uh, like if you are finding a bigger Fibonacci number, this unnecessary part will increase drastically. So using dynamic programming, this kind of unnecessary calculations are minimized. Okay, then I will explain some more simple examples. So here, say you are in this kind of grid. So we will come across these examples later on as well, but I will show you the importance of this. Right. Here, if we are going from this corner point to the exit square, right? think you have fire in your building, right? You have a fire in this building, right? So you have to avoid fire and go to this exit scar, right? In a case of emergency, the best way is to uh, use the shortest way, right? Okay, so to find the shortest way, you can use dynamic programming in this case. Right? If there is fire in any of the rooms, you cannot enter those rooms. That is a normal situation. So, and another thing is, you have to always go right, like this way or down, right? Because you have to, uh, that restriction should be given in the problem statement. But in this case, I will take it as that. So you can only go right or down. So every uh, turn, you will be getting closer to the exit. So if we uh, do calculate for all the paths in here, that will have a big number of paths, and that will take more time to calculate. Like here, we have only 6 scores, so that will not be a big task. But if we do this with the bigger grid, that will be much complicated. So here, what we can do is we can another dynamic programming approach. I will go through these things later. We can uh, find the shortest distance to any score in this grid, right? So let's say this one to come here, it takes only one move, but this is not happening. So that should be indicated. So we are taking a grid similar to this. So at the initially, this one will be here, and she cannot reach the bottom score. So I will mark it as -1. And then to come this score, it will take only one move, right? If we consider this score, she cannot come this way, but she can come from this score. So it will take only one move more than this score, right? This is 1. And she can, if we consider this square, she can come only through this one. So this is also like one more. Sorry, this should be 2 because two movements are there. So if we consider the exit one, we have to take the minimum out of these 2 rooms and add 1. So this will be 3. You have to calculate from the beginning to end, right? This is another dynamic programming approach. So you are solving it for the other rooms as well in order to obtain the uh, shortest path to the uh, exit room, right? That is another dynamic programming method. I will go through the technical words later. So that is another way. So I will move on to the technical things a bit, and then come back to the examples. So I told you about these things. In a dynamic programming, we would see some kind of overlapping subproblems or optimal substrates. I will explain these things. So subproblems are like in the previous example, you have found the Fibonacci sequence of 5 multiple times, right? 4 multiple times, but you found the Fibonacci sequence of 7 only once, right? So subproblems might be overlap. Like these things we had to find it more than once, right? So it is very like time consuming. No, your problem will not be in optimized shape. Therefore, we can avoid these things. So, uh, like in a dynamic programming uh, problem, you would see some kind of overlapping subproblems. And another thing is there should be a optimal substructure. That means uh, the final solution could be constructed using, let's say, the same problem asked for a subproblem. Like here, what is the seventh Fibonacci number? The subproblem is what is the sixth Fibonacci number and what is the fifth Fibonacci number. These are the two subproblems that you do ask. Like in the grid case, you have been asked for the optimal path from the enter square to in square to out square, right? But in this case, you are finding paths to optimal path to go to any of these squares, right? So to find the path to optimal path to the exit square, you have to find optimal paths up to this square and this square, which are the squares that the exit square can be reached, right? So these are two subproblems that we can solve here. Then using the subproblems, you can find the answer for the main problem, right? So in here, to solve this square, solve for this square, you have to solve for this square. So this is a subproblem that helps to solve another subproblem. So this kind of a structure, if this kind of a structure they are in is there in a competitive coding problem, most of the times you could use dynamic programming techniques, but I will discuss in towards the end of the session that this property can be used to a kind of trap you in a dynamic programming trap, right? So like they can give a different problem, most probably uh, like some kind of a mathematical problem or something that might be seen like a dynamic problem, right? A dynamic programming problem. For instance, this Fibonacci one. Uh, the dynamic programming approach might not be the best way to do the Fibonacci problem. Right? There are many other ways which are very optimal. But for instance, to learn dynamic programming, this Fibonacci example is very good. So I took it. Memoization and tabulation. So these are the two main approaches that you can use in dynamic programming, right? So I have already discussed these two approaches. I will remind you and I will let you know what are those two. So first one is memoization, so or the memorization method. So memorization method means you would need the solution for some set of sub problems. You will have to calculate those solutions again and again, like in Fibonacci problem, right? So you are solving from 7, like starting from 7 and then go to 6 and 5, so on, right? So this is the top-down approach. You are starting from the final solution that you require, right? This is most probably a recursive approach, right? You know what the recursion is, a function calls itself inside the function. Right. This is kind of a recursive approach. So you might be able to do a dynamic programming problem this way. Right? This involves memoization. So we will define some kind of a memo variable. It will be sometimes this it will not be this way, but we are using dictionaries most of the times because dictionary keys are stored in stored as a hash table. So in a hash table, to find a key, it does not take much time. So if we store the answers as a dictionary, we can easily recall them. Right? If we want 5, when we go into the dictionary, it will go straight away to 5 because to 5 it has a specific place in memory for 5. Right? So that is how this works. So we are going from the main answer or the main problem to the sub problems. While solving sub problems, we store the solved answers in memory. Like in the first case, we need 5 and 4. So we will solve starting from 3, right? So answer for 3 will be stored in memory first. Like first we know the answer for 1 and 2. Then we will store for 3, then 4, and so on. Then when we need answer for 4 here, we can take it from the memory, right? So the tabulation approach is a bit different. I will explain it here. So what we can do is we can make a table. For the Fibonacci sequence, we can make one column and like if we want the nth number, we can use 1 by n table, right? 1 rows and n columns. So here we can do it like this. This may look so simple for this example, but for some problems, yeah, I have problem. Yeah, I have a question. So yeah, I will discuss that as well. The question is how to make sure memory limit does not exceed. So I will discuss about this question when we are discussing how to choose between top-down approach and the bottom-up approach. So in this case, we are building 1 by n grid. Okay, I will not go deeply in how to select this grid because when we are discussing the problems, you will understand that. Okay, here we have the first two terms. So we are going to build on this array recursively. So when we will recurse from 2 to n, right? Numbers, otherwise 3 to 7, right? So when we are finding, we will start from the bottom. Here the approach is bottom up, right? Not top down. So we will start from 3. So third term can be constructed using the two previous terms. So we can straight away calculate the third term. Then using the last two terms, we can calculate the fourth term and save it is array. So those values will be saved automatically. Then the fifth term, then with these two, the sixth term, and then with last two. So we can use kind of a simple iterative scheme to do this bottom-up approach. So these are the two main approaches. I think you can see the difference and if you can solve a memoization problem, if you can solve a problem using memoization, most probably you will be able to use tabulation as well. Okay? The other way is also true. If you can use tabulation, you will be able to use memoization as well. So those two are just two approaches, but both of them are dynamic programming. So you can use both in most of the cases. Right. Then how to start solving the dynamic programming problem, right? So first you have to define the states of a problem, then the transition between states. I will discuss this using the fire escape example. So this is the exit, this is the entrance, right? Let's say there is here you have fire. So in this problem, here the state is somewhere you can be, right? This is the state. So I will number these things. So 0, 0 is a state. 0, 1 is another state. Then 1, 1 is 1, 0 is another state. After that, 1, 1 is another state. Likewise, you can go on and on. 2, 0, 2, 1, 3, 0, 3, 1, right? So these are the main states. So like it's like if you are developing the solution, what are the sub problems you are looking at, right? Then you have to see the transition. That is very important. In Fibonacci, you are adding up the previous two states to obtain the new state, right? So here you are looking for the possible entry scores for a certain score to calculate the minimum or the optimal route, right? So optimal route length, right? So this transition is important. This could be very complex when we go to some complex dynamic programming problems, but first we will understand with some simple problems, and then you can understand the complex problems as well using dynamic programming. So this is very important. You have to define the states clearly, and then you have to define the transition between states clearly, and you have to select what is the approach you are going to take, like top down or bottom up. Okay, it's the first thing I wanted to discuss. So okay, let's see another important thing, how to spot a dynamic programming problem, right? So here you should have some practice as well, but I will take you through some simple stuff that will help you to differentiate between dynamic programming like problems where you can apply dynamic programming and you can. I will mainly tell you how to identify dynamic programming problems, right? So normally dynamic programming problems looks like one of these problems, but yeah, one important thing I forgot to mention, the dynamic programming is not a category of problem itself, right? It could be, but we cannot call it just a category. Dynamic programming is a method of solving competitive programming problems, but not a problem category like you might say graph theory, right? Graph theory we have some problems, but graph theory is a concept as well, but we have problems specified in graph theory category, right? So another thing, we have string problems, right? Like what is the longest common prefix? So that kind of problems are there. So this is another category. This is another category. If you consider about dynamic programming, we can use dynamic programming in these categories as well. So when you are you are solving a graph theory problem to find the shortest path in a graph from one grid to another grid. This has many approaches, but let's say if you are using dynamic programming to reach the last grid, first you have to find the shortest path to reach the adjacent edges, right? So if you know how you can reach these two in minimum number of ways, you just have to add one or the path length to these two and check what is the minimum, right? Uh, that way you can easily uh, solve this kind of a problem. So in graph theory, you can apply these things. And after some time, I will discuss a string problem where you have to edit one string to be another string with minimum number of edits, right? You have to make sure two strings are equal. You have to find the minimum number of edits that is required to make the two strings equal, right? So these are the two approaches. Then the first one is optimization. Uh, yeah. Uh, the first one is optimization problems. So dynamic programming is everywhere. So if you spot this kind of problem, you can try to apply dynamic programming. Okay. Optimization problem means where you have to find like minimum path distance or maximum number of profit that can be earned. That kind of situation you can use dynamic programming in many cases, right? I don't say you must use dynamic programming, but sometimes you would be able to. Let's say another kind of a problem, that is problems with combinatorial like possibilities. I will give you an example with the same one. Like if you have like the same problem, this is the in, this is the exit. If you have fire here, right? So you here and okay, let's say fire is here, right? You have to calculate the number of ways you can reach the exit, right? So starting from here, you can go to this square in one way, right? So from this square, you can go to this and this. So you have one way to go this square, you have one way to go this square, right? Then from this square, you can go down and right? So here you can go from one way. Here also you can go from one way because you can come here by one. Again from this square, you can go here. So you can go here using another way. So you have to add one to this, right? So you can go to this square by two paths. So if you consider this one, you can go to this square, right? There's another one way. So if we consider this one as well, there are another 2 ways. So all altogether there are 3 ways. So you can find the number of possible paths that are that are possible to reach the exit, right? So this is another thing. So another thing I forgot, like if we have this kind of a problem, I just use this to demonstrate it. But in this case, if we are finding the shortest path where you can only go down and right, yeah. So, someone has raised the hand. If you have a problem, please put it in the chat or ask, right? That's fine. Okay. Yeah, in the fire case, if you can only go down and right, it is obvious that you have a maximum number of, like you have a maximum or minimum or must number of squares that you have to go to reach the exit. That means anyways you have to go 3 squares this side and 1 square down, right? So no matter what path you use, you have to go 4 times, like in a path of length 4. So that is the thing. So that problem has only one answer, so you can straight away take that answer. But I hope you understood that for this problem, the counting path problem, you can use dynamic program. So I hope you understood the thing. But if you have further questions, you can ask. I used that example before for the easiness of understanding. If you have confused there, please take this one as the example, right? Okay. Then here you have a framework, like some steps to identify a dynamic programming problem, right? When you encounter a problem, first you can see whether your problem can be divided into sub problems, right? Uh, in other words, you can see whether it can be divided into some overlapping sub problems, like where you will always have to find the same answer or same answer again and again. So dynamic programming will definitely optimize that in that case. After that, you have to check for optimal substructure, like, or in other words, optimal subproblem, right? Then after checking for the substructure, then you can determine a state representation. That means in this case, where you are, or in the Fibonacci example, what is the term you are at, right? Then you can try to establish a recursive solution, like recurrence relation, like in Fibonacci sequence. Or if we think about this one, we can say to solve this one, we need to solve this one and this one. To solve this one, we need to solve this one. To solve this one, we need this one and this one, right? So uh, in that case, you have like here final stage, we need these two. We need these two for this stage. We need these two for this one for this stage. Likewise, you can establish a recurrence relation. So recurrence relation means you are using the top bottom approach, right? Not the sorry, yeah, you are going from the top to the bottom, right? So, or the top-down approach. Top-down is the word that we are calling. So, the other one is bottom-up approach. So, if you are using the bottom-up approach, you will not be using the recurrence relation. Right. These are some examples that will help you to identify the dynamic programming problems. I will first tell you what knapsack problem is. You might already know the knapsack problem. You will have some kind of like, let's say 0-1 knapsack problem. There are some variations. The most common problems we have many variations. This is in that category. So knapsack problem, there we have 0-1 knapsack problem. That is the basic version. So you will have, let's say, robber, someone like, let's say a thief, right? He has a bag. The bag has capacity of, let's say, 50, right? You are given the capacity of the bag, and in a house there are many items, right? Let's say there are n items. Like in this case, I will say 3 items, right? So each item has a weight and a price, right? Price and weight, right? So you will be given a given an array of prices and weights. So if you think as the thief, what you have to do is you have to maximize the price. But in this problem, so for the thief, it is important what you will pick up and what you will not pick up, right? But here they are asking only the maximum price that you can collect, the optimal price, right? Let's say there are 60, 100 and 90 weights. Sorry, the prices are, then weights are 10 for this, 20 for this, and 30 for this, right? You can see that the optimal way is to take these two. So with that, you can easily maximize the value. So the maximum value will be 190. That is the answer. So for that kind of a problem, you can use dynamic programming. I will show you the answer later, the approach later. Then the sequence alignment problem, like let's say you are given a DNA sequence. So like A, B, C, D kind of thing there, not the DNA names, but I took only 4. So then AB, this kind of sequence is there. So after that, let's say you need to align A with A, B with B, C with C, D with D, like this. So, but you have another sequence which has A, C, C, A, C, C, D, B, B, right? You have some options. You can shift this entire sequence right, or change one, from here, right? You can change one from here or one from here. Likewise, you have to make sure that the two sequences are same. I will discuss one problem kind of like that. So to sequence alignment problems, you can use dynamic programming. Then the shortest path problems. I told you many examples about shortest path problems. So in a grid or in a graph, any kind of a graph, most of the cases you would be able to use dynamic programming. So then partitioning problems. So partition problems. I will discuss a partition problem as well. Say you can cut a rectangle into integer length pieces. Right? Let's say you are given 5 by 3 rectangle. So I will divide this into 5 and 3. Right? Your task is to divide this rectangle into squares with minimum number of cuts. You can only cut through this integer levels, right? So you can only cut through these lines. You have to cut this into squares, right? So in this kind of a problem, you can, what you can do here is you have to cut through any of these lines, right? These two or these two, right? So you have to select a line out of these 6 lines, right? If we cut from this line, we will have this and this, like 2 pieces. You have to make those 2 pieces are squares, right? Make sure that those 2 pieces are square. So if you select this line, I told you, if you select this line, you have 2 below and 1 above. If you cut on the horizontal side, like if you cut from one of these 4 lines, if we select the last one, this one, you will have 4 by 4, 4 by 3 square and 1 by 4 square. If you select this one, you will have 3 by 3 square and 3 by 2 square. So if you know the, if you know the minimum cuts required to cut these squares, like 3 by 3, you need 0 cuts. For 2 by 3, you will need maybe 3 cuts, right? If you know those two, you can add them together. 0 plus 3, right? And you can see for which cut you will need the minimum number of further cuts, since you have solved all the sub problems in this case. I will discuss this problem later in a deeper way or the clear way. This is another one example where you have to partition something, right? Okay, then I will go into that space management question and the top-down versus bottom-up approach, right? I already told what these two approaches are. The top-down has recursion with memoization. Bottom-up has iterative solution building from base cases. Like we build the Fibonacci sequence from the first 2 terms. And this case, we started from the last term and then go into the first terms, right? Those are the 2 ways. So there are advantages and disadvantages. So main advantage in top-down approach is it is easy for you to think. So I would say you can make the top-down approach code and then ask some AI tool to convert it to bottom-up if you need. That way, you can do that easily. Or you can, okay, maybe you will be able to straight away take the code. That's another case. But top-down approach is easy to think. most probably easy to think than the bottom-up approach for some problems, right? But there might be very clear bottom-up approaches, like for the Fibonacci sequence problem, right? So you have to be careful in those cases uh, to select what is the best approach. So iterative solution building from base cases. That is the uh, bottom-up approach, right? Okay. Then what are the advantages of bottom-up? I told you that this one is easier to implement, right? Then here, this one is more space efficient. They say like that, but like most of the times these two will take some kind of a similar space, but this one is space efficient. Why? This uses recursion. So in recursion, you will store something like here you will store that. Oh, I need to remember that I am finding the Fibonacci sequence of 7. So you are going to remember that you are going to find the Fibonacci sequence of 6 and then 6 and 5, and under 6 you will again remember 5 and 4. Like that you will use the stack very much, right? Up and up. So if we take this for a big number, you will have a large stack. So considering the stack, this will be very big, but considering the this one, the storage or the memorization, this memory will only contain the first few terms, first 6 terms. In the tabulated approach also, we will have a array for the number of terms. So in these two, the memory used always almost same, but here the stack usage is higher. So since we are using recursion, so in that case, you can prefer the tabulated method, but when you are implementing the code first, try to go for memoization, and then if you want, you can, if it's easy, you can straight away do the tabulation. But uh, but in other cases, you can start from memoization, right? Uh, so when choosing between top-down and bottom-up approaches, the key facts are problem constraints, space considerations, and implementation. So ease of implementation might not be a big thing these days. So, but space and time are the most important things. So I think the one question that you asked included some kind of space overflow, right? Like it it exceeds the space, right? I would say there is a space limitation in every uh, competitive coding problem. So you have to understand what for which problem uh, what is the size of space that we can use, right? That will be like you can calculate that. So by experience you can get an understanding. If I talk about the time in a program, you can do operations up to around 10 to the power sorry, up to around 10 to the power 7 or 8. In between this kind of number of calculations can be done most of the times. Or in the technical terms, we are speaking about time complexity of in ON or like big O notation, right? So in this case, if you are finding the Fibonacci sequence of like we'll see say n equals 10 to the power 7, this will not work most of the times because you are storing 10 to the power 7 numbers, right? You can test these things, but I don't think this will work because uh, it is a huge ask to store this kind of a numbers. If you are storing some number below 10 to the power 6, I think this will work as well, but below 10 to the power 6, if you are storing numbers, that will work fine. But if you are storing some true false values, you will be able to store more than 10 to the power 6, like up to this 7 or 8. That will be possible, right? So in dynamic programming, you cannot do much thing to minimize the memory usage because you are once you decide to use dynamic programming, you decide to use the memory instead of time. Like you have to do this uh, deal or the like once you gain time, you will lose space, right? You can minimize the time or space. So you have to keep the balance between those two. So you can choose dynamic programming for problems where the constraints are like you are using if you are using tables, you have to make sure that table has less than 10 to the power 6 entries like that. This kind of consideration should be done. Then the time considerations and space considerations. Let's say you have 10 to the power 5 here and another 10 to the power 5 here. Then that will be 10 to the power uh, 10 to the power 10, right? This will not work most of the times. So also due to the time and due to the space, this will fail. Therefore, you have to consider this, and if you encounter this kind of a problem, there should be a uh, much optimized way to solve that problem. That's the thing. So you have to carefully look at those things. Then I will uh, I discussed these things already, so I will go to the code straight away. So, yeah, here I have the Fibonacci code. Yeah, uh, yeah, this is it. Using the top-down approach. So we have the memory dictionary. Then I am defining a recursive function which is called helper. Once we call this Fibonacci top-down function, it will define this helper function. And inside the helper function is a recursive function, so it calls itself. Right? See here, we are defining, we are giving the number n. Then if number n is there in the memory, it will just return the number because we have the answer already, right? So if n is less than 2, that means we are using 1 Fibonacci sequence. So n is less than or equal to if it requests the first or second term, it will return 1 because we know first and second terms are 1, right? After that, memo in memo n should be like this. Means if the code reaches here, you don't have that Fibonacci number in your memory. So you need to calculate that Fibonacci number. Therefore, we are going to calculate the nth Fibonacci number. So you just have to assign a new key to that key named n. Then you have to calculate helper n minus 1 plus n minus 2. In this case also, it will do the same steps for n minus 1. So finally, it will return the nth Fibonacci number. Then what you have to do is, in the main function, you need to return the Fibonacci number for n. So you define this helper function and then call it. That's it. So I did this function definition to show you the Fibonacci bottom-up approach and top-down approach all together. So in the bottom-up approach, you are just defining an array which has all zeros. So you will have array and then db1 equals 1, right? Because you have db0 equals 0. So 0 and 1 will be the first two terms and then go on. But when we call the index 1, the term will be 1. Index 2, the term will be 2. So this is the same Fibonacci sequence. It's similar to the Fibonacci sequence we defined earlier. But this starts with 0 because in the array there's a 0th index. Right. Like it's the 0th term, right? Then we are starting from second term to nth term. We are just adding the last two elements to then we put it in the next term. Finally, we need to return the last term. So if we use the bottom-up approach, I will go to this extension and run the code and check. Yeah, here you have all the expected outputs. So if we try it with this one, it will also give the right output. Right? Hope this is clear. So I will move to the next slide. So that is another one, bottom-up versus tabulation, bottom-up versus like memoization versus tabulation approach, point change problem. So this is a very common problem. You have to give the minimum number of coins requires to change a given number, right? Let's say you need to change 11. So you have coins 5, 3, and 2, right? So with 5, 3, and 2, you have to take, first you have to take 5 out, right? Then you will remain 6. Then you can take 5 out, but if you take 5 out, you will not have a coin to make 1. So you will have to take 3 out, then 3 will be remaining, and so you will have 5, 3, and 3, right? So in this case, 0 will be the answer. So this case you need 3 coins to make 3 coins to make 3 coins to change 11 rupees, right? So that's it. That is the coin change problem. So in this case, you would think the best way is to, if you can remove 5 from 11, then just remove the biggest coin, right? until it's greater than 2 times 5 or something like that, right? Then you have to figure out the thing. But let's say if we take this kind of example, 6, 1, or okay, 6, 1, 3 and sorry, 1, 2, 3 and 4 are there, then you have to make 6, right? Okay, no, not 2. Yeah, if we do like this, if you take 4 out of 6 early, you will have 1 coin and 2, right? To make 2, you will need 2 ones, right? So these approaches are called greedy approaches, like you are always going for the maximum possible coin. So this will not work because here you will get the answer as 3, 3 as the answer. But in this case, the best option is to use another approach. Like here, you would use 2, 3 coins. So you can change the amount of 6 by only using 3 coins, right? Sorry, only using 2 coins. So greedy approaches will fail here. So you have to be careful to not to use greedy approaches in this kind of problems, right? Greedy approaches might help you in some other problems, but not in problems like this. So you have to carefully look into the method you are using, right? So in the coin change problem, let us say that 11 example, I will use the bottom-up approach first, right? So I will divide this into like around, if there is 12, that's fine. Yeah, 11 are there. I will make another one. So you will need 0 coins to change 0, right? I have to change 11. I have 2, 3 and 5 coins, right? I am going to change 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Okay, I will discuss about the memoization first. Okay, in order to change 11, finally I can use a coin 2, 3 or 5, right? So I can see uh, what is the minimum number of coins required to get 9 plus 1, right? So another way is get 8 in minimum number of coins and add 1, or get 6 in minimum number of coins and add 6 in minimum number of coins and add 1 coin. So because you can end the coin selection with 2, 3 or 5, right? So in this case, you will have to solve 6, 8 and 9, right? Okay, then we will look at the 9. To make 9, you will have to make 7 plus 1, or make 6 plus 1, or make 4 plus 1, right? And then you will go down and down this way. So finally you will find the optimum number of coins that is required to make this happen. That is the memoization approach. So you will not have to build all these things in a paper or something. You just have to do this algorithm and then find it, right? But in the tabulation approach, what you can do is you can first put -1, not -1. First, let's say we will put infinity here because we are going to minimize. So infinity is the largest number. So we are just putting infinity, right? Okay. We have all infinities here. With that, we will start. Okay. For each number starting from 0, we are using the bottom up here. So we can start from 0 here, right? Yeah. Here you can see you can make 2 with only 1 coin, right? You can make 3 with only 1 coin. You can make 5 with only 1 coin, right? Then you will look into, you will go to the next step. Then you are looking for 1, right? But 1 is not there. They like uh, to make 1, you have to you need to have infinite number of coins. In other words, you cannot do that. So you cannot move. You can try to move ahead. Infinity plus 1 is infinity, but 3 has 1 in it, right? You are putting these numbers. You need the optimal solution. So uh, the if the optimal solution you are getting is less than the optimal solution it has, then you will be putting that number in it, right? Since this box has 1, you are not going to put infinity here. Here you have infinity. Here for 6, you have infinity. So no changes. Then you will go to 2, right? Then from 2, you can add 2 to take 4. So here is 1, then 1 plus 1 is 2. 2 is smaller than infinity, so you put 2 here. Then 1 plus 3 is 5, but you already have 1 here. So no need of putting 3 here or 2 here, right? You need 2 coins if you use 2 and 3. So you are not going to put it here because you have an optimal solution already. Okay, after that, I will change the color. After that, you have the 5 coin, right? You can go from 2 to 7. Okay, this will take 2 steps. That's how you can solve this. After that, you can go back to this and okay, go to this one. So you are iterating through the uh, number of change or number of iterating through from 0 to, not from yeah, from 0 to 11 or something, the final amount, while iterating inside that you are checking for each and every coin. So this order is determined by looking at the constraints and the problem, right? So here you are at 3, so you don't want to go 5 because it has 1. To go to 6, you will need another 1, so it will be 2, right? So here you have solved the problem I asked earlier, making 6, right? You need only 2 iterations if you have 3. So after that, from 3, you can go up to 8. So for that, you will need only 2 coins, right? Okay, here you can put 2. Then you will go to 4. From 4, you can go to 6, no need. From you can go to 7, no need. You can go to 9. Yes, you need to go to 9. It's 3, right? Uh, then from 5, you need to go to 7. it's already done in the optimal way. From 5 you can go to 8, it's also done. Then to 10 you can go. Here you will have 2, right? So 5 and 5, 2 coins. Okay, then go to 6. 6 to 8, no need. 6 to 9, okay, from going from 6, that will take 3 coins, right? But 9 has 3 coins. Then 6 to 11, you need only 3 coins. Okay. Then you will start from 7. 7 to 9, no need of doing that. 7 to 10 is also not needed. 7 to 12, 12 is not here. So you are not checking that. So you have to include that consideration in the code as well. Otherwise, it will call for something not available in the memory. That will be a problem, right? So you just neglect 12 and then move to 8. 10 is optimized. 11 is also optimized. 12, 13 now, 12, not 12, 13 is not needed. So we neglect that. Go to 9. Then try for these ones. 11 is not there. Go to 10. Nothing is here. Then 11, nothing is here. So we are done. Then this is the answer array. So you have to select the last one and return, right? 11th term. So answer will be 3. That's how the coin change problem is done. So I will show you the code for the coin change problem. So I'm not sure. Yeah, minimizing coins is here. Here you have to make 11 in 3. Okay, I will make a new test case. You have 3 different values of coins. Then you will be making 11. So what you have is 1, 2, and 5, right? Not 1, 2, and 5. 2, 3, and 5, right? So the expected output is 3. I will run that. That is passed. So what is the approach I am using? It is bottom-up approach. So in the bottom-up approach, for I in range 1 to target plus 1. That means it's going from 1 to uh, like target plus 1, right? Target means the final value that we should do. We have 0 plus infinity values. That is the array we made earlier. Then for 0, we had 0. That's it. Then we are iterating for each element. So, and another important thing, first we are making for every coin, we are making it 1. Like here you can see 2, 3, and 5 are coins. Those are the only ones here, right? You will make it 1 first, and then you can do the iteration. Like from 1, you are going to go for the available places. Okay, so we are doing like that. Then we are going to get the minimum value which is already there, and yeah, this way you can do it. This approach is bit different, but this one also works fine. This is not the approach that I discussed. It's bit different, right? Then this minimize coins top down approach, it has a helper function and a memo, right? So memory and helper will help you to go through this function. So here what we do is what we discussed earlier. We are solving for the answer minus each and every coin. Like for coin in coins, each and every coin, you are taking the minimum of memo value and you are solving for target minus coin plus 1. Right? In this way, you are updating the memory. Right? So if we print here, print what should be print? Target and memo target, not memo yeah, target, coin and memo, right? So if we run this, okay, you have to change this one as well. Top down, right? So if we run this, you will have this first the uh, after all these iterations, first it will find the target as 3 because target is getting reduced one by one. So the coin is 2. The memory has these infinity values, right? After that, the target is 3. Coins, number of coins, not number of coins, the considered coin is 3. So for 3, you will have 1 in the memory. So it will return 1. Likewise, 5, uh, like target is 5. Here you can make 5 by 2 operations, but after looking at the coins, it will figure out this is not 2, not 5, but 1 in some iterations. You can see here it's 2, here it's 2, but in this iterations it has fine. It should be 1, right? This way it will get better and better and better. Like you can see the evolution. But when we look at this finally, for 1, it will be infinite and the other answers are there. So you can take any of the answers. The interesting thing here is, here you don't have 10, right? Because why? You are going from top to bottom. So when you start from 11, there's there cannot be 10. Why? Because you are reducing the coins. No, so you are not reducing 1 from 11. You are starting by reducing 2 straight away. So after 11, you will have 9, right? Then 8. But in this case, first you are reducing 2. So you will go deeper and deeper in that, deeper by coin 2. So first you will have 11, then you will have 11 minus 2, then 9 minus 2, then 7 minus 2, then 3, 5 minus 2, then 3 minus 2, right? After that, uh, in this from 3, 3 minus 2 is here. Then if you consider about 5, 5 minus 3 is there. So then you will have 2, right? Likewise, you will build this array. You will see the order that you are reaching these numbers for the first time. So this is how the memoization works in the this approach. So you would see these both of these approaches are quite same, but this is easy to be understood by us, but this is very short, but it includes much thinking than the other way. So I will go to some examples to make sure that you got these things, and I will discuss those and uh, I will just discuss those examples so you can try coding them. I will show you the code as well, but that is not very important, I guess. Okay. First of all, I will introduce you a problem. The shortest path in a grid. Uh, uh, Example, that is shortest path in a grid. Find the shortest path from the top left corner to bottom right corner of a grid with obstacles, right? Uh, you can only move right or down at any point in a point in time. Right? Some cells are blocked by obstacles. So that is the problem that you have. So you have to uh, do this you have to do this thing using any method that you like, right? Okay, here you will have to use kind of this is very clear if we use the bottom up approach. So I will take an example grid. Yes, I will go to the problem that I have and then take the example from that. Right? Okay, here I have a problem like um, uh, shortest path in grid bottom up, right? This is the number of rows and columns. Then we have this grid, right? One, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, like this, 0, 1, 0, 1. Right? Okay, I will take this back to yeah, I will take this here. So I will have this kind of a grid, right? Where I cannot enter this cell, this sorry, this should be wrong. Again, this is in the knapsack problem, right? I will go to this. Sorry for that. I will start this one here. Okay. Yeah. Here you cannot reach these two squares and these two squares, right? Okay. For like you should notice that for any given approach, this should be 7, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So if you can move only right and uh, down, then you will also find that always find that if there exists a path or many paths, the distance to reach the uh, last square equal. So this is not an actual problem. This is kind of a problem that I made to explain, right? So I will change this problem a bit. I will find the number of paths. So that's it. Then I will start from this point. Then to go here, I have one path. I will start from the 0. Right? I will remove this point as well. Uh, okay, now we are going to solve this. Yeah, here if we can go to every state using transitions. So I will start for I in range 3 or I in range number of rows or j in range 3, right? Number of columns. So I am going to start from that location. So first I will make this 0 and then I will like we will go from 1 to 3, right? Yeah, 1 to 3 and 1 to 3. So first of all, I am going to go through these two lines, right? From here to bottom and here to here. Right here to go to this, it will require 1, 2, 3, right? Since you don't have any obstacles, you can go. But here you will have 1, 2, and you cannot go here, right? If you have some scores afterward, you cannot go to those as well. So this will be infinity, right? Infinity, infinity, infinity. So you have to go through these two row and column first. After that, you can do this iteration. So it will first go to 1, 1, right? Then 1, sorry, 1, 1, then 1, 2, then 1, 3. Okay, we'll see 1, 1. 1, 1 has its value as a cross. So 1, 1 can be reached by this one and this one, but the problem is 1, 1 has an obstacle. So you cannot reach that. You can neglect that easily. So then you will go to 1, 2 square. So 1 is the row number, 2 is the column number. So you are coming here. So actually I am counting the number of paths. So what you have to do is okay, let me erase this. Number of paths are needed. So number of paths is different, right? So I will use this. Yeah, here you have one path from here to here, here to here, and then yeah, you will have one path. Here also you will have one path, and for this one you will have 0 paths. Okay, here also you will have 0 paths to come to this one. Then you will go here. Then you can come from here and from here. You are going to add these two things together. Here you will have one path. Here you will have 0 paths. Okay. Then you are done with these things. Right. Here you will have, okay, I told you that you will not have an obstacle here. Right? Then you will go to 2, 1, right? 2 is the row. So you are going here. Here you can add these two. So you will have 1. Then here you can add these two. You will have 2. Here you can add these two. You will have 2 again. Right? Because you cannot come from the above square. Then here also you will have 1. Here you will have from up 2, and from this side 2 there will be 3. Then from these two you will have 5. So I think you got the way of doing that. You are going from the square to square and then build the number of paths. So finally you can output the number of paths, right? So that is the simple method to solve that. Okay, I will take you through a knapsack problem. So in knapsack problems, I hope you got the 0 and 1 knapsack problem. So I will show you how to take the knapsack problem down, right? Here I will take a very simple one. So where you have three, you have three items and 5 is the capacity. So 3 items will cost like one is 100, the other one is 60, and other one is 120. So this will weight 1, 2, and 3, right? So the selection will be these two. So you have to find a way to solve this problem, right? If we see at the this knapsack problem, right? So you have to determine the best parcel that you can obtain under a certain way, with or without this bag. I hope that you didn't get the point I told. I will explain it this way. So you have 3 bags, right? And you have the weight up to this. Okay. You have 5 weights and 3 bags. So I will say this is first, second, and third bag. And this is the weight inside your knapsack, right? Okay. So with the first bag, what you can do is you can take the first bag, or you can leave the first bag, right? So if you are taking the first bag, then what will be the weight of your parcel? That will be 1, right? So if you are taking the first bag, then uh, your parcel or the for the first bag case, you will have 1 and the weight will be 1. Then for weights above 1, also you can have 100, because you only have the first bag, right? So you will fill all these squares with 100, because that is the optimum value, right? For 1 and larger than 1. Okay, then you can decide whether you take this bag or not, right? So if you take this bag, right? If you take this bag, you will increase the uh, weight by 2. So if you are going to take this bag, for 2, you will have the optimum answer as 60, right? Then you cannot take this bag with answer 0. Okay. Then if you decide, if you are going with taking the bag, then what will happen? Like, you are completely independently checking for the second bag only. But here you have to go for the optimum solution. So you can decide for weight 1, you can keep the 100, right? Okay, this one is not important. You can take this 2, or what you can do? You can do it like this. You can take this bag with, like, you can take the bag 1, and you can just avoid taking bag 2, right? Or just avoid taking the second object, right? What is the optimal solution? So the best way is to, if you have if you have only 1, then the best way is to, what you can keep that as it is, right? you can avoid taking the second bag. But when it comes to this place, so you can think that this way, the weight of the second bag is 2. So this row represents the weight, right? Okay, this row represents the bag. Okay, I will explain this way. This represents the bag, right? Then what should I do? I have weight 3, then I have bag 2, right? I want to see whether I can pick the second bag, or I can just drop the I can or I can decide not to pick the second bag, right? So I am explaining this in a very minimal way, but this algorithm will minimize it further and further. So here you are just reducing, here you have 3, no? You are reducing 2, like the bag's weight itself. So you will have 1. So you are looking for the 1 row, right? Here you will have the best amount that can be obtained with weight 1. But if you pick up the bag 2, you will have weight of 3, uh, because you are getting an additional weight, right? So what you will do is you will pick up the bag with this, right? So here you can see you are going to pick up the bag. So you will have 160 of weight here, right? After that, you will have the same amount of weight. So you can see with weight of 3, the best amount you can reach is 160 up to now, right? Then you will check for this. You will have 100 because 3 has weight of 3. For this also you will have 100. For this you will have 160. Oh, yeah, you can have 160. And then for the weight of 4, there also you can only have 160. Why? Uh, uh, is that true? No, right? Because here you have 3. Uh, like after reducing 3, you will have 1 here, right? So since you have 1 here, you have to check the best value out of these things. So you will see that 100 is there. So you can add 120 to 100. Then you will have 224 this point, right? Then if you check for this one as well, you will have 220. So like this, you can use a table to find out the best combination or the maximum value that you can reach using the knapsack problem, right? Uh, so this is how it is done, but this is not the best optimized algorithm because this will have quite a lot of iterations. That kind of problem is here. So, but you can study the dynamic program approach, which is optimized for the knapsack problem. I will not go further in this problem. I will move on to kind of a different set of examples, so we can quickly discuss them as well. So here I am going to discuss the edit distance problem. This is in the CSCS problem set. So here you have to find the minimum number of edits or the operations required to transform one string into the other string, right? So the you can do like you are given 2 strings, you are going to transform one string into the other string, you can do these operations. You can add one character to the string, remove a character from the string, or change or replace one character from the string. That is the problem. You have to find the minimum number of edits required, right? So I will take the example in my code. So let me see what is the example in my code. Edit distance. So I have love and movie here as an example, right? So this is straight away taken from CSCS problem set. So the first test case is this, right? So I will make a DP array, right, for these words. So I am going to make this equal to this word, right? So I need to define the number of rows and columns. So for this length and this length, I will take rows and columns, and then I will explain the method or the logic here, right? So I will take 5 plus 1 rows and 4 plus 1 columns. You can interchange the number of rows and columns if you want. That actually doesn't matter because edit distance to make this one to this word or do the otherwise, you will take the same number of operations, right? Therefore, the vice versa is also correct. So you can interchange the word or interchange the grid as well, right? Okay, I will put the words here. This is the first word and this is the second word, right? Here I am solving some kind of small sub problems. Like I am going to make M with L first, right? Here in this box, I am going to make M with L, right? So this is nothing. So if you are making nothing from nothing, you will need to edit 0 things, right? If you are making L from nothing, you have to make one changes. You have to add L. Here you have to add L and O both. So you have to do 2 changes, 3 changes and 4 changes. So you can straight away, if you are making nothing from M, you are like, if you are making nothing, right? You are making the word in string in this set. So you are making nothing using M. You have to remove one words. You are making nothing using MO. So you have to remove 2 words. If you are making nothing from MOV, you will have to remove 3 words, right? So you are making nothing. Okay, then we will check for the other words. So if you are making L from M, you need to change one word, right? One letter, right? So here, the number of edits required to make nothing using L. Sorry, make L using nothing, right? So if you are making L using nothing, you just have to calculate how much do I need to make nothing using M, right? So nothing using M. Then you can use that to make L. So you need to reduce one letter and then add one. So you will need 2 operations. But the case here is you can take nothing and nothing because these two are similar and then interchange the letters. Like you can remove M and put L. So you have to check 3 boxes to determine the option here. So you have to see at this one, and this one. Since these two letters are not equal, you will have to interchange the letters. So first it will have nothing and nothing. These two are equal. So you just have to change these two letters. So I can add 1 to 0. Right? What I just have to do is take the minimum value from these three squares and then add 1 and put it here. Right? Since these two are not equal, we will see what happens when those are equal. Right? If I want to make L from MO, then I will have to do 2 edits, right? Remove MOO and add 1. So I consider these 3 squares and L and O are not equal. So I will have to do one more operation here. So if I am making L with this, I will have to do 3, 4, and 5. Right? These are the optimal operations to make L using M, MO, MOV, MOVI, and MOVIE. Right? After that, I will consider LO case. Right? Then here, if I want to make LO with M, I will have to change M to L and then add O, right? So then I will take the minimum out of these squares and put 2 here. Right? If I want to make LO with MO, you can see that these two are equal. So if these two are equal, you can keep them as it is. Right? Therefore, you can take this square, especially this square, because these two are equal. You can look at one letter reduced from the first word and one letter reduced from the second word. Both should be reduced because you have a similarity here. So you no need to remove one of those. So those letters. So you can see here you have 1. So you don't have to change anything here. So you can just put 1 here, right? Because O and O are similar. So if we make LO with this, then 2, 3, and 4 will be changes will be required. Because here you have more letters, so you have to remove them. In this case, if we are making LOV with this M O M, then you have to change M and add O and V. Right? Then if you are making with MO, you have LO with 1 change and then you have to add V here. Right? So you will have 4 changes for this. Then MOV and LOV, you just have to do, you can see these two letters are similar. So since they are similar, you are going to look with one reduced version. So here you have 1, so you don't have to do it. Sorry, right here also you can remove I and do the thing. Then here also you can remove E and do the thing, right? That's the way. So you can see if these two letters are similar, the answer will be this corner 1O, the minimum of these two minus 1. Sorry, minimum of these two plus 1. We are taking the minimum value out of those things, right? If these two are not equal, then you have to take the minimum of these 3 squares and then plus 1 to get this square. That is how this problem is solved. So you can slowly go through these kind of dynamic program problems. Then if we have M only, you will have 4. Then E is there. So